Alright, the first concept that we need to clarify in this topic is the idea of magnetic flux. So we can introduce it by way of an analogy. So we can think of, for example, the amount of grass in a lawn as being the product of the density of grass and the area of the field, or area of the lawn. So for example, a 30-meter squared lawn has a density of 120 plants per square meter. How many plants are there? We can figure it out by just using the density of grass, which is 120, times 30, which is equal to 3,600 plants. Okay, so the amount of magnetic field is what we call the magnetic flux, and that is the density of the field times the area in question, and the density of the field is another word for magnetic field strength. So we can say field strength, which you'll remember is the density of the field lines, times the area in question. Okay, so the symbol for magnetic field strength or flux density is B, and the unit is the Tesla, which has a symbol capital T. The symbol for the area the field passes through is capital A, and the unit is meters squared. And the symbol for magnetic flux is the Greek letter phi, and the unit is the Weber, which has the symbol WB. So we can write phi is equal to BA. And the units are going to be the same as Tesla times meters squared. And the word for that unit is the Weber, which we can call the Weber. So we can compare different situations here. So in A and B, we have a higher field strength in B, which we can tell by the fact that the field lines are closer together. And in question 2, if we look at flux, we have more field lines in B than we have in A. So B has the greater flux. The areas are the same, but the density is higher for B. In which case is the field strength highest, A or C? It's A. The flux in A and C, well, we've got 12 field lines here, and we've got 12 field lines here, so the flux is the same. They are equal. In which case is the field strength highest, C or D? Well, it's going to be D, because we have more field lines in the same area. The flux is highest in C. Sorry, D, of course, because we have more field lines in total in that area. So to summarize, magnetic field strength symbol is B, and units are Tesla. Magnetic flux symbol is phi, units are Weber, and phi is equal to B times A. So looking at these examples, if you have a circular loop of radius 3 centimeters, and it's perpendicular to a magnetic field of that, what's the magnetic flux through it? Well, to work this out, we want to find the area, which is pi r squared, and 0.03 squared, and we want to multiply that by the field strength, so phi is equal to BA, which is equal to 0.02 times pi times 0.03 squared, which is equal to 5.7 times 10 to the minus 5 Weber. Okay? Okay, in this situation, there are no field lines going through the loop. So in A, phi equals 0. In B, where it's at a 45-degree angle, we just need to multiply the full flux by the sine of the angle, because only a proportion of the field lines are going to be going through, not all of them. So we take our answer from part 1, and we multiply it by, let's just check that we are in radians here, in degrees. So let's change that to degrees. So then it's going to be answer times sine 45, which gives us 3.998, which is 4.0 times 10 to the minus 5. So the point here is that it's the number of field lines actually passing through the surface that is the flux, not just the magnetic field strength times the total area. Okay, so that's flux. Next we'll be looking at Faraday's law.